in our lesson 3.4 where we are actually going to be graphing, today we're going to talk about when we're given a specific domain. In other words, remember, what is domain made up of? X values. When they give us some X values, we're going to substitute each one. So each domain value is going to get substituted into the function and we'll get our Y value. And we practiced some of that already in earlier lessons in this. In fact, we just did in lesson 3.3. And then after we get that Y value for that specific X value, once we have the range value that goes with the domain value, we will write it as an ordered pair. So I kind of had you starting to practice that yesterday on the worksheet. Once you get them, put them together as an ordered pair, and then we'll graph them on the coordinate plane. So here's our first function that we're going to graph for a specific domain. So here's our domain. They say when x is -5, when x is -3, when x is 1, and when x is 4. There's only 4 domain values. So how many range values should we get? 4. 4, yeah. So we have to get 4 Y values to go with those 4 X values. Well, we're going to get it so that we would have the function rule by itself on one side of the equation, and then all we have to do is work with the function rule in the middle of our table. So in other words, we want this Y by itself. So what would we have to do to get that Y alone? Trey?
Subtract. Would we subtract that -2? Add. No, yes, subtract -2.
We could subtract a -2x, but remember, when a negative number is being added, we can really just easily undo it by adding its opposite. So we just really need to add 2x to both sides, which really is the same as what Trey just said, subtracting a -2x. This is just a cleaner way to do it. And now we have y by itself on the left side, and we have 3 plus 2x on the right side. So remember, this part right here is what we call our function rule. We can get y by doing that. Take the x value times 2 and then add 3. So we're going to put that, and in fact we're going to, because addition allows us to do this, we're going to switch those two around. We're going to let the 2x go first. You can have it either way, it doesn't matter. That's our function rule. And we're not going to draw our other column for our y value yet until we see how much room it's going to take us to show our work in this table. So we're going to try and work without a calculator. So we're going to substitute in, like it said up above, we're going to put in for x, the given x value. So you just did this. Substitute in to the function rule, the given x value. We do multiplication before addition, so what's 2 times -5? -10. So now we have -10 plus 3. And now we're ready to say, oh, okay, I don't think I need any more room to show my work. My y value is what? What's our y value? -7. So -7 is our y value. So we now have what ordered pair? What ordered pair is that? -5, -7. Okay, now we'll go in and take our next domain value that they want us to do. They want -3 substituted in for x. And yes, you have to show this work. 2 times -3 is -6. And we have to add 3 to that -6.
-3.
-3. So what ordered pair is this? -3, -3. Okay, now we are going to move on to doing it for +1. Okay, 2 times 1,
2,
2. 2 plus 3,
5,
5. Ordered pair,
1, 5.
1, 5. Okay, this is a good point for me to stop and say, okay, you people who don't like to show work for all of them, is there any sort of a pattern going on there? In the Y, look at the Y. Is there a pattern going on? Okay, what is that pattern then? How many of you would have thought maybe anybody, like jump ahead and say, I'm not going to show work, and they had the Y value before we did this last one? Ray, what do you think the pattern is? It's going down by 2.
Like that, right.
You get from -7 to -3. 7 below goes up to 3 below. What did the temperature just do?
Right.
Went up 4, didn't it? Now it's at -3, goes up to 5 above. What did it just do? Actually went up. Everybody's going all the way around to 7, 9. Went up 8. 3 to 0, and 5 more is 8. Okay, so it went up 4, then it went up 8. So should we just assume the next one's going to go up 12 then, or what? No, we're not going to, because here's the deal. There's really no definite pattern going on over here in the X's either. So you're going to be really careful. When you want to be lazy and not show the work and say, okay, I see, okay, I think the next one's going to be 1, and then the next one's going to be 5. Because you think you have a pattern established, you might want to get lazy and do that. Don't do that, because we aren't sure, and especially if we didn't pick out over here if there was any sort of a pattern going on, and there's not. So we got to be really careful.
You know how you said it was 12?
I said if we went with what we thought was going to happen.
It's not 12, but it's really close to 12.
It's close though, huh?
I know what it is.
2 times 4 is
8.
8. Oh, you guys are better at adding when they're both positive. 8 plus 3 is 11. Okay. It's really close, you're right. But it's not. 4, 11 is our next ordered pair. So you have to show work for all of them. Don't shortcut it. Don't get lazy. Don't feel sorry for your pencil. Okay, now we're going to go onto our graph, and we're going to graph all of those ordered pairs. So we're going to graph ordered pair -5, -7. So how do we graph ordered pair -5, -7? Rose? Use the X and the Y axis. So where do we start? At the origin. So what do we do from the origin for -5, -7?
Go back 5.
Go to the left 5.
And then down 7.
And then down 7, and we put a point. And you go ahead and do it on your graph while I'm trying to see on mine. And put a point. Okay, go ahead and graph the other 3 points also now. And then you can look up and verify with mine after you have all your points graphed. Oh, we got a problem here. 411. That kind of goes off the graph, doesn't it? Oh, well, we'll just put it up there where we think it would be about. Okay, so again, you want to check to see that you have them in a good location. Just by looking at the domain, let's go back to that domain. Just by looking at the domain, is this a discrete function or a continuous function?
Discrete.
Why is it discrete, Isaac?
Because it's like the dotted lines, and it's like
Just by looking at the domain, there's no lines in the domain. Just by looking at the domain, how do we know it's discrete? Everybody needs to be engaged here, because I'll tell you what, this is going to be important. You'll lose points on the quiz because you didn't understand this part. Cameron, right.
It's discrete because it has distinct planes and not a grid or sign showing that there's more in between.
Absolutely. When the domain is given as distinct values, they listed 4 specific x values in the domain, right here. They listed 4 specific x values in the domain. They did not have to write it as a compound inequality or even as a simple inequality. When there are no inequality symbols involved, then you know it's discrete. Okay? So when they give us distinct x values, written in a set like that, in set notation, they say, here's your domain, we know it's discrete. Well, what do we know about, and then when we're done graphing a discrete graph, do we connect the dots? No, continuous is connect the dots, isn't it? So we're done graphing this one. We don't even need to draw line segments or connect the dots. We would say it's done. Because, let's put that beside our graph. This is what we call a discrete graph. We have distinct points. Yes, Isaac.
Are we gonna have to say if it's a discrete or continuous in the homework?
In your homework. Not necessarily. When this comes into play, this helps you make the decision whether you should connect the dots or not. Connect the points or not. That's when you're gonna. So you may just have to process it to decide if you should connect the dots or not. There are gonna be times we do, and there are gonna be times we don't. So even if it doesn't tell you in the directions to identify, it might be a good idea just to be in that habit. Okay. Any other questions? Okay, let's go to the back. We're going to do another one. We have f of x equals, then we have a negative sign, and then we have some bars around an x, and then we have plus 2. Can anybody tell me what those bars around that x say again? What does that say? What's that about? Ariel?
Absolute value.
Absolute value. Oh, what does absolute value mean?
Distance from x.
Not the distance from x.
Distance.
Distance from 0. How far is that number from 0? That's what that is saying. Okay, so remember f of x is the same as what?
Why?
Y. So we're going to say, you know what, let's just replace it with a y, because in our ordered pair, that's how we typically think about it. One is x, the other one is y. Okay, what do you think? Do you think we have a discrete situation here or a continuous?
Discrete.
Cameron?
Discrete.
This is discrete because they distinctly gave us how many x values do we have to work with? 5. So we should have 5 points on our graph, shouldn't we? Okay, this one already has f of x by itself. We're going to replace that f of x with our y so we can see if we have our function rule. Do we have our function rule already? Do we have to do any rearranging? In other words, can we get y by doing everything over on the other side? Yeah, y is by itself. When y is by itself, you guys, we have to understand that this right here, over here, is what we call the function rule. It's what we do to x that will help us get the y. So we're going to write that function rule down right here in our table. Then we're going to transfer all of our domain values to our table. We have a -6, a -3, a 0, a 3, and a 6. Okay, so now we do our substituting steps. So negative, absolute value bars, -6 in place of the x, absolute value bar, add 2. Don't shortcut this here. So what is the absolute value of -6? In other words, first thing we're going to do is get rid of the absolute value bars. It is 6, isn't it? So this negative sign that is right here is coming over. That's coming over. I just brought this over right now. That's right here. The absolute value of -6 is 6. We're getting rid of the absolute value bars. We're down to those two things to,
Is it -4?
so we have a -4 for our y. Okay, now we bring our negative sign down, our absolute value bars, substitute in -3 for our x. The negative sign is out front of the absolute value bars. It's not part of our absolute value, so we have to bring it along. What is the absolute value of -3?
Positive 3.
+3, and then plus our 2. So what's our y value this time?
-1.
-1. Now we have a 0. Negative, absolute value of 0. Do the substitution first. The only thing we're going to get rid of in this step is the absolute value bar, so the negative sign comes along. What is the absolute value of 0? 0. Is there such a thing as a -0?
No.
What's another thing we can say in place of that word negative? The opposite of, what's the opposite of 0? 0. So what we really have here is 0 plus 2. What is 0 plus 2?
2.
2. Okay. This time it kind of looks like there might be a pattern going on. But should we count on it?
No.
Probably not. We probably should substitute in, even though you might want to. Say, I'm going to go with the pattern. Okay, so we substitute a +3 into those absolute value bars this time. Negative sign comes along. What's the absolute value of 3?
-3.
No. How far is 3 from 0? 3. Absolute value means how far am I from 0? 3 is 3 units away from 0. -3 plus 2. -1. According to the pattern, that might not be what we would have expected. And we have one more to do. Substitute 6 in for our x into our function rule. Bring our negative sign along. How far is 6 away from 0? 6. Plus 2. -6 plus 2. -4. Okay, let's write all of our ordered pairs over here. What do we have? Here we have -6, -4. Here we have
This is gonna create a box.
a box. 0, 2. I want you to write the ordered pairs. 3, -1, and 6, -4. And now you can go graph those 5 ordered pairs on a coordinate plane. Did we get a box?
No, got triangle.
I'm not sure what we get a box out of a 2-dimensional graph anyway. A box is 3-dimensional. What did we get?
Triangle.
Well, we didn't even get a full triangle, did we?
Monochrome.
We have a
Upside down cross.
upside down V, don't we? Really what we have here. Do we connect the dots?
Nope.
Why not?
It's discrete.
It's because it's a discrete graph. We were given a distinct domain. It said these x values only. So we do not connect the dots. Okay, so let's put that beside here that we have a discrete graph. We do not want to connect the dots. We just wanna admire our upside down V not being connected. Okay, any questions about this one?